This lesson is on properties of graphs of functions. We're just going to start with some interval notation so that you know how to write intervals down and are aware of what these symbols mean. So I've given you a few examples here, and I'm going to write it in a form that you're more familiar with so you can see where they've come from and hopefully be able to create them on your own. So this first one here, the interval is showing from negative infinity through to 0, and you'll notice that they're rounded brackets. The rounded brackets mean does not include. And negative infinity basically is telling you it's the largest negative number you can think of. So basically the number line keeps going and going and going on forever. So the other way we can write this is x is less than 0. Right, that would represent the same set of numbers as the interval notation. Next one here, we're going from negative 3 to 7. So same round bracket, so it's not going to include those. So we can also write this as negative 3 is less than x is less than 7. And the next one you'll see they are square brackets. Square brackets mean it includes it, so it will be less than or equal to. So here we've got 2 is less than or equal to x is less than or equal to 13. And notice that every time we use infinity, it has the round brackets. That's because infinity is not an actual number. It's more of a concept. So we can never say it includes infinity because infinity is not a number. This last one here, you'll see it has a mix of the brackets, and that can happen. So here you'll have that x is greater than or equal to 8. Our first definition for properties is an interval of increase, and that is the subset of the domain where the graph rises. Now, remember that when we talk about the domain, we're writing it with a notation that shows it's a set of numbers. So subset indicates that it's a part of that domain. It could also be the whole domain. That's still within the definition of subset. So another word that you could use in place of subset is part. So we could say that it is part of the domain where the graph rises. So we're looking, remember, like we're reading, so everything's going to go from left to right. So we're looking for intervals that go when going from left to right, the graph increases. And we can tell by looking at this that we've got a parabola, and it's starting here at negative 3 that the graph starts to rise. So we've got this interval that covers from negative 3 and going on into infinity. So our interval of increase goes from negative 3 to infinity, and it does not include negative 3, because if you look at that specific point, if you drew the slope right next to that point, it would be a perfectly horizontal line, so that's not increasing right there. So we don't include negative 3. And now we'll look briefly at the subset of the domain where the graph gets lower, so the interval of decrease, which is the opposite definition of the previous one. We're still going to look left to right, just like we're reading, and only this time we're looking for areas where the graph is getting lower. So again, we can look at here where we know that there's a change. So the part where it's getting lower is from negative infinity to negative 3, so it's on this side here. And again, it does not include that negative 3, right? Because that part of the graph is where there is actually no change occurring. It would be a horizontal tangent. So we have an interval here of negative infinity to negative 3. And you'll notice that even if we combine the two previous ones, we still would have this hole in negative 3, right? We don't have negative 3 as increasing or decreasing, and that's okay. So now we're just going to look at odd functions. It's a type of symmetry that we're looking at here. Okay, it's a type of symmetry. So we're looking at odd symmetry right now. And it has odd symmetry when the function will be the same or congruent when it's rotated 180 degrees around the origin. So in other words, if you stuck a pin in the origin and it rotated the graph 180 degree turn in either direction, obviously, and it would still be the same graph. So in this case, we've used the example f at x equals x, so we just got a straight line. And this is the algebraic definition of odd functions. So just to keep everything clear with this example, I'm just going to put brackets around this. Oops, sorry about that. I don't know how that happened. We're going to put brackets around this x here, just so that we can show easily when we're plugging in the negative x on the inside versus the outside of the function. So if we're looking for f at negative x, that means when we plug in x, we're going to plug in negative x. So there's negative x going inside the function, which you guys know that this is just negative x. And also if we're doing negative x with the negative on the outside of the function, then we've got this here, which we can see is the same thing. So we know that this is a true statement for this particular function, and it has to be true of any of them that have an odd symmetry. Now we're looking at the even function. It's a different type of symmetry. In this case, we're looking at the function when it is flipped in the y-axis. So that's essentially to mean that we have a mirror line here. So we've got a mirror line in the y-axis. So if you were to put 1/2 of the function in a mirror, then you'd end up with the whole function, which you can see would happen with this one. And we also know that this is the algebraic definition that has to follow for any even function. And you might recognize the function I've chosen for this one here is f at x equals the absolute value of x. Okay, so we need to check to find out first, let's see, f at negative x. That means I have to plug the negative x on the interior of the function. So here we go. But we know that the absolute value symbol means that we are going to get a positive value no matter what x is, which means the negative inside here doesn't actually matter. So this is, in fact, the same thing as the absolute value of x, which, as we can see in the definition, is f at x. So algebraically, we can also see that this example is an even function. And finally, we're going to look at continuous functions. So a continuous function is one that has no holes or breaks in it, which basically means that you can draw the graph without lifting your pencil. So I've given you the parabola example here. This is an example of a continuous function. So here is a continuous function. Okay, we can draw it in one swoop. It goes all the way from negative infinity to positive infinity, which doesn't actually have to do. It just has to be continuous from beginning to end. There are no holes, no breaks here, so it's continuous. And then the graph on the right here, this is a discontinuous graph. So it has points of discontinuity. Okay, is discontinuous. So it has points of discontinuity. We can see here. This is an example of a break right here. Okay, there's actually two of them. This is a break as well. And then you can also see there's an unfilled circle here, which means that this is a hole. There is no value for positive 4 for this function. So this is a discontinuous graph in 3 different parts. So at negative 4 and positive 2 and positive 4, you have points of discontinuity.